Hello friends, let us start with our fifth chapter, non-traditional machining. This is also known as unconventional machining. So, before going in the detailed processes of this non-traditional machining, let us understood what are the limitations of our conventional or traditional machining processes. Okay, so when you talk about the tool material, it should be 30 to 50% harder than the workpiece material. But sometimes what happen, if workpiece itself is very hard and there is no tool which is harder than the workpiece, now there is a question mark, which material used as a tool material. Okay, or sometimes the material has a very poor machinability, that you will not get the proper machining on the workpiece with the conventional machining processes. Then also you will find the limitations of our traditional machining. Suppose you are interested to make a very small holes, say less than zero point 0.1 millimeter in diameter, then also the conventional machining processes cannot do that. Again, complex shapes, automations, then machining of highly brittle materials. Say for example, I want to drill a glass, then it is not possible with the conventional machining processes. Okay, then if I want to machine a complex concave curvatures, then also it is not possible by the conventional machining processes. So therefore we require something new machining processes or non-traditional machining processes to do these jobs. And which are these processes? So see here we are having these basic unconventional machining methods. These are ultrasonic machining, abrasive jet machining, electrochemical machining, chemical machining, laser beam machining, plasma arc machining, then electron beam machining. Right? We will see it one by one. So in this video we are going to understand about USM, that is ultrasonic machining. Okay. So see here the schematics of this ultrasonic machining here. So here is the abrasive slurry tank. This is a fixture on which the workpiece is mounted, and this is the tool given with the feed force, right? And it is vibrating. The tool is vibrating and also feed with the feed force. And you can see the gap between this tool and workpiece. In this gap, we are applying the abrasive slurry. Okay, so these are the transducers to have these vibrations of the tool. So this is the simple uh, schematics of the ultrasonic machining. Let us see how the material actually removed in this process, ultrasonic machining. Okay, you can draw this diagram. Let us see the schematics view of material removal. So see here, this is the tool, or which is also known as horn. This is our workpiece. Okay, this is the tip of the tool, and see here this gap between the tip of the tool and workpiece. In that gap, we are providing this abrasive slurry, and as I told you, the tool is vibrating with ultrasonic vibrations. Commonly, the frequency is around 20 kilohertz, and the amplitude is ranging from 50 to 20 microns. And at the same time, tool is given a constant feed force. See here. Okay. So from one direction we are applying this abrasive slurry between the gap, and we can have the dislodged chip or removed material at one side. Okay, so see, the basic process of this ultrasonic machining involves the tool, which is actually made up of the tough and ductile material, is continuously vibrating with very high frequency. See, this is vibrating very high frequency, and the continuous slurry of abrasive, right, is fed in the small gap between tool and workpiece, and at the same time tool is fed with the feed force F. So what happened? These hard abrasive grains, so these are spots are the abrasive grains, fractures the hard and brittle work surface, resulting in the removal of work material in the form of small particles. Okay, and the tool material, which is tough and ductile, wears out with a very slow wear rate. So, students, one thing we have to keep it in mind when we are learning about these non-traditional machining processes, that is wear ratio. Okay, wear ratio is what? So, actually, how much material removal we are obtaining on the workpiece divided by how much wear occurred on your tool material. Simply, it is a ratio of volume of material removed divided by the volume of tool worn out. This is the wear ratio. And each process we will try to understand this wear ratio. Okay. So here, if this is the work removed from the, or material removed from the workpiece, and this is the tool worn out, see here, then the ratio is known as the tool wear. Okay. Uh, it is wear ratio actually, right? So this is the schematics view of material removal, and I already described how it is taking place. If you want to see the mechanics of ultrasonic machining, so what is happening there? We can describe the mechanics of ultrasonic machining in the following way. Number one, the hammering of abrasive particles on the work surface by the tool, right? Abrasives are having impact on the uh, workpiece by the tool. Then this impact of free abrasive particles on the work surface. Okay, after happening of abrasive particles on the work surface, they are causing the impact of the free abrasive particles on the work surface, and finally the erosion due to the cavitation. We can describe the mechanics by writing these 3 points. Now, if you want to find out the volume of work material removed or removed, we can write it as Q is proportional to the this capital V into Z into nu, where V is what? The volume of work material removed or volume of material dislodged per impact. Z are the number of abrasive particles making impact per unit of cycle, and nu is the frequency. Okay, so Q is proportional to the V into Z into nu. So these are the things here I mentioned. Now, if you look at the diagram, the first diagram I show you. So on the top of that diagram there was a transducer. Okay, see here. So this is a transducer. So what is actually function of this transducer? So transducer in the ultrasonic machining, which will convert the electrical energy into the vibration or vibratory motion of this tool by using the magnetostrictive principle or the piezoelectric principles. So here, what is magnetostrictive transducers and piezoelectric transducer? We will see in short. Okay, so actually the magnetostrictive transducer, which are generally made of the permalloys. The composition of permalloy is what? 45% nickel and 55% of iron. When they are exposed to a strong magnetic field, they are going to change their length. Okay, when they are changing the length, we will get this the feel of vibration. Okay, and if you talk about this electrical piezoelectric transducers, what they are doing, when the electrical current applied to this piezoelectric materials like quartz or lead zirconate titanate, they will increase in the size, and when the current is returned or when the current is removed, they will return to its original size or nominal size. So this is how they are changing their length, and that will give us effect of vibration of the tool. Okay, then look at this tool horn, or this is also known as horn, simply tool cone or the horn. So these are also known as the concentrators. These are also known as the concentrators. These are the various types of controls, concentrators. So what they are doing actually, this tool cone or horn, they are amplifying the mechanical energy produced by the transducers. So horns mechanically amplifies the vibratory energy to give the required force to amplitude ratio. Understood what this tool cone is actually doing? It will amplify the mechanical energy which is produced by the transducer, and will get the required force to amplitude ratio. Okay, we can attach these various types of concentrators to the tool tip. Okay, by means of screwing, or we can braze it. Okay, here written, the tool tip attached to the cone by means of silver brazing or by screwing. So see, this is the exponential concentrator, this is the conical, and this is the stepped. These are the types of concentrators we can use at the tip of the tool. Okay, then if you talk about the abrasive slurry, so typical abrasives which are used in the USM are aluminum oxide, silicon carbide, or the boron carbide. But here see, aluminum oxide wears fast and it good for glass and ceramic, whereas boron carbide is popularly used abrasive which is harder than the silicon carbide, but which is costly than silicon carbide. Okay, sometimes we can also use the diamond dust for getting the good accuracy and surface finish, also the cutting rate. Okay, now the fluid, if we talk about the fluid in the abrasive slurry, so the most commonly used fluid in the abrasive slurry is water. Okay, water is most commonly used fluid in the abrasive slurry, but other than fluid we can use the benzene, glycerol, or the oils we can use in the abrasive slurry. If you look this graph, the viscosity of this slurry versus the material removal rate, you see, when the viscosity this slurry goes on increasing, the MRR goes on decreasing. Okay, so this is the thing about the viscosity of slurry. So viscosity goes on increasing, you can see that the MRR is going to decrease. Now let us talk about the tool material in this USM. As there are impact loads are acting on the abrasive particles. So Newton's third law, with that, equal and opposite reaction force will produce by the abrasives onto the tool material or onto the tool simply. So there are having chances of the brittle fracture of tool material also, isn't it? So as it is removing the material, and abrasives are again causing the impact on the tool material according to third law of Newton, then there will be definitely the fracture will take place on the tool material also. So hence wear of the tool is going to happen. Okay, so that is the reason why we are not interested to use the hard tool material here. That's why we are using the tough and ductile or soft ma- material, tool material, and which are commonly used in the USMR, the copper, brass, mild steel, etc. Okay, let us see the advantages of USM. Of course, these are used for machining of very hard and brittle materials, and the very famous example of this USM is machining of or drilling of the glass or ceramics. Okay, so next advantage, what? It is not affected by electrical or chemical characteristic of workpiece. We can produce a hole of any shape. Okay, it has high speed moving parts, therefore working is not hazardous. No high speed moving part is are involved in this equipment or in this machining process. That's why it is not hazardous. It is safe. Okay, now what are the limitations of ultrasonic machining? So of course the low MRR is there compared to the other machining processes, unconventional machining processes. USM is having low MRR. Then the depth of hole produced are the limited. Okay, the tool wear is high. As tool wear is high, sharp corners are not able to produce. Flat surfaces cannot be produced at the bottom of the cavity due to the ineffective slurry distribution. Okay, we cannot go at the bottom to produce a flat surfaces as there is an uneven distribution of this slurry. So these are the things about the ultrasonic machining. Okay, so we'll discuss the next process in the next video. Thank you.